what we're going to do is we're going to move our discussion of the mole along and start talking about what we call stoichiometry. And all stoichiometry is the use of a balanced chemical equation to calculate the amount of reactants or products that are required or present, and we can also look at percent yields and other things. Now, stoichiometry rests upon the law of conservation of mass and our law of definite proportions. The idea that matter is not created or destroyed, and so everything I have before, I'll have after. So, just a reminder for our balanced chemical equation, right? So here we have for the combustion of methane, it tells me that 1 molecule of methane would react with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of water. Now, molecules are where reactions take place. Reactions take place between molecules. However, suppose we said Avogadro's number of molecules rather than just 1 underwent our change. Then it'd be 1 times Avogadro's number of methane reacts with 2 times Avogadro's number of oxygen to produce 1 times Avogadro's number of carbon dioxide and 2 times Avogadro's number of water. Or 1 mole of methane reacts with 2 moles of water to produce 1 mole of carbon dioxide and 2 moles of water. So what this tells us is that in a balanced equation, to go from the amount of one entity to the amount of the other, I have to do it at the mole level, and to do that, I can use a mole ratio. And this is the crux of stoichiometry. When I'm converting from the amount of one reactant to another, or a reactant to a product, or a product to a reactant, however I want to go, I have to use a mole ratio to go from the amount of one thing to the amount of another, because reactions take place between particles or groups of particles, which we'll call, say, at the moles of particles. So let's look at a couple of examples. So in our first example, we'll start off easy. And here I have the decomposition of our potassium chlorate. And it asks how many moles of oxygen can be produced if 12 moles of potassium chlorate were to react. So when we do these, the first thing we have to do is we have to remember to follow all of our proper procedures, where we write down our given, then we'll write down our required, we'll write down an equation, can substitute and solve. So the first thing we need to do for our given is we always want to make sure that we have a balanced chemical equation. And we want to remember we're going to go from the moles of my potassium chlorate to my moles of oxygen using a mole ratio. Okay, so first we write out our balanced equation, and it is strongly suggested that you write down the given right under the balanced equation. So we were told our moles of potassium chlorate, so I'm going to write that right under my potassium chlorate in my balanced equation. We're asked for our required for our moles of oxygen. Again, I'm going to write what I require right underneath the balanced equation, so that it helps me to keep track of my information where I'm going. So, as we stated, to go from the moles of one thing to the moles of the other, I need a mole ratio. So I'm going to take my moles of my potassium chlorate and multiply by a mole ratio. So my moles of oxygen are going to be equal to my 12 moles of potassium chlorate times the mole ratio. My mole ratio comes from my balanced equation. Since I'm going from moles of potassium chlorate, it'll go on the bottom of my mole ratio. Since I'm going 2 moles of oxygen, it'll go on the top. The numbers in my mole ratio, remember, come from my balanced equation. So in my balanced equation, I have a coefficient of 2 in front of the potassium chlorate, so a value of 2 goes in my mole ratio. In my balanced equation, I have a value of 3 in front of the oxygen, so a 3 goes in front of the 3 moles of oxygen in my mole ratio. So now at this point, now that I have substituted everything in, I'll just solve, and I see that this reaction would produce 18 moles of oxygen. Let's take a look at another example. In this case now we have ethine is going to undergo a reaction, and we're asked how many moles of oxygen are required. Now, whether I'm going from reactions to products, or from one reactant to another, or from a product to a product, we use the same technique. And we use the same things. So we have a balanced equation. First thing we do, we write out our given. Again, write it right underneath the entity in the balanced equation. And then we want to write out our required. Again, we want to write it right in our balanced equation. Okay, and as stated before, to go from the moles of one thing to the moles of the other, we use the mole ratio. So I want to know my moles of oxygen. I have moles of ethylene. So then, now I'm going to start here. Okay, 45 moles, my mole ratio. Because I'm going from moles of this, it's going to go in the bottom of my mole ratio. And because I'm going to moles of oxygen, it goes in the top. Now our coefficients, again, our numbers in our mole ratio come from our coefficients. So in my balanced equation, I have 3 moles of oxygen, so in my mole ratio, a value of 3 will go. In my balanced equation, I have 1 mole of ethylene, so it has a value of 1 in my mole ratio. So now we just solve. Now, we don't measure out moles when we have substances, but we measure out masses or volumes. And so if I start off with the mass, and I want to go to the mass of a product, then we follow the same process, except now we add one step. Because I start off with a mass, we have to, just because we start off with mass, means that I still have to go from moles of A to moles of C. I can only go from the amount of one thing to the amount of another at the mole ratio level. Well, my mole ratio comes from my balanced chemical equation. So if I'm starting off with a mass, then to get to moles, remember we have to divide by our molar mass or multiply by the inverse of the molar mass. And then once I get to moles of my product, to go from moles to mass, all I would do is multiply by the mole mass. Okay, so let's take a look at this example. I have potassium chloride that can be made in the following reaction, and we're asked how many grams of iodine are required in 26 grams of my potassium chloride. Just like before, even though we've added a layer of difficulty, we always start off with our given. So we always write out our balanced chemical equation, and right underneath our balanced chemical equation, we write out any masses or volumes that were given. And then we identify our required. Now, one of the givens that we have always, remember, especially when we're dealing with masses, is we have our molar masses. And that's because these come from our periodic table. Okay? Now, just because I have masses doesn't mean that I change. We have the same pattern. We have to convert our mass of potassium chloride into moles. Then we have to convert our moles of potassium chloride into moles of iodine. And then we can convert our moles of iodine into a mass of iodine. Remember our process. Okay? So therefore, we can write out our equation based on this, because we have our roadmap, where my mass of my iodine is equal to my starting point, my mass of my potassium chloride, times the inverse of the molar mass, which gets me the moles, times my mole ratio, which gets me the moles of iodine, times the molar mass of iodine. Once we have our equation, then we can substitute our values in, okay, and we can use our units to check, and then we can solve.